Hey, welcome to another lunch dev session. We got a talk this time uh with Alex Anderson. I got that right? Anderson?
Yeah,
Okay.
Anderson.
Perfect, perfect. I never know. It's like you say these names for the first time and it's like, did I get it right? And it's like I think, there's always the ones that I think I'm going to get right that I get wrong. So, Alex Anderson's going to talk about React in 3D. It's going to be awesome. We got some people here, so there might be some questions that you hear but not see video of. Maybe you will see the video. We'll see. But we got a fun little setup, and I'm super excited to see what you have for us, Alex. So without any further ado, take it away.
I hope that you brought your 3D glasses because we are going to be diving in to React in 3D. So, my name is Alex. Like Michael said, you can find me on Twitter at ralex1993. That is my face spinning on a cube. Ooh. And we're going to be talking about the basics of 3D graphics, and then we'll dive into how to make 3D graphics with Three.js very simply. And then we'll talk about using React 3 Fiber to do 3D graphics, but even simpler if you're familiar with React. So let's get started. The very first thing that we need in order to do any kind of 3D graphics is a scene. In this case, we have this scene with my React in 3D text and then my face spinning around on a cube. But a scene, just like the real world, you can't actually see anything in a scene unless you have lights. So here, I don't know if you noticed those two little cubes pop up, but those are my lights in this 3D scene. And they illuminate everything to make it so you can actually see what's going on. But then, just like in real life, in order to actually see things in a 3D scene, you have to have a point of view. You have to have a camera. So, lights, camera, like that. And then once you have that, you can actually animate things and make things move and change. Action. So, with those basics in place, with lights, camera, and a scene, you can actually start taking what's in the scene and rendering it to a view, making it so that your user, whoever's browsing on the website, can actually see what you're displaying. Before I go any further, I can turn off the anaglyph effect to make it so that it's not quite so 3D. Is that helpful? Is that better? Or should I keep it so that it has the red and blue there?
This is probably better for me.
Okay, I'll keep the anaglyph off from here on out, but when I show you the slides in the end, you can switch it on and off by pressing the A key. So you can check out the slides on your own later. Are there any questions up to this point?
I was gonna ask where are my 3D glasses? That's about it.
Yeah, I need some myself too. Okay, so moving on. Once you have your scene, your camera, and your lights, how do you make it so that you actually take the things that are in the scene and render it to the screen? And this is what we call rasterization rendering, where we have a object, and these objects in 3D space are designed or designated with points in 3D space. So here I have points for 0, 0, 1, or -1, negative 0.50 and 0.5, so on and so forth. Let me see if I can make that any bigger. There we go. So now you can see those numbers just a little bit better. And these correspond to points in 3D space. So you have an x-axis, you have a y-axis, and you have a z-axis. Or you could have a y-axis up and a z-axis in whichever, but they represent these points in 3D space. In order to actually create a 3D object, you draw lines between these points and create what are called faces. So here are the lines, the edges between the points. And then we can turn these lines, these triangles, into faces. And then these faces represent the actual object as it's moving around in 3D space as we rotate these points. So there it is. Now that we have our 3D object defined with these points, faces mapped out so that it actually has some structure to it, we can point a camera at it and start rendering it. And the way that we do that is we take a look through our camera, we look at every single pixel that we're going to be rendering, and we see if there is something there. And If there is supposed to be something there, then we figure out what color it's supposed to be. And we draw that color, that pixel, and then we move on to the next pixel. And we do that 60 frames a second. Now, this is obviously a very simplified brute force way of doing it. There are a lot of rendering techniques which make this faster, more effective, that produce more realistic results. But at its most basic, creating a 3D renderer involves finding out what color each pixel is supposed to be based on what objects are in your scene, what lights are in the scene, and which direction the camera is pointing. So in this case, here's our camera, and oh dear, my camera stopped working again. It's supposed to automatically move, so let me just refresh the page again. It's a little finicky. Okay, there's our renderer. Oh, it's just not moving. Oh, that's a bummer. Anyway, here's the camera. We can see the camera's looking at this, and it's figuring out what pixels are supposed to be at that particular point. Man, I wish I knew why it was behaving that way. Okay. Any questions about rasterization rendering? I'll see if I can take us back. Nope, the camera's just not moving at all. Ah, come on. Okay, questions? Awesome. So we're going to deal with the deficiencies of the slide deck as we go along. But for right now, let's talk about materials. Materials are the things that give our objects their color, their appearance. Once we have our 3D object defined, we have to have some way of telling whether it is a red sphere in this case, or whether it's blue, or whether it has some image like that image cube of my face. We can see here that we have a light shining on this red sphere, and materials respond to light in different ways. So in this case, it's a very diffuse object that reflects some of that white light back to the camera as a lighter color. And then down here, it's a darker color. And then we get the true color of the sphere kind of here in the penumbra of the shadow. But there are other settings which we can set on the material of our object to make it so that it appears in different ways. So here it is. We've got some, it's kind of difficult for me to point out specific parts, but we've got some glossiness. We have a metalness versus plasticness quality to it. All kinds of different settings that affect the way that these spheres capture that light and transmit it back to us. In addition to having these different settings that we can set on materials, sorry, the camera's still broken, so we've got to bear with me while it loads. We can assign images to objects. So this is a little spaceship that I have, which is a pre-created mesh that includes an image texture that goes over it. And there are ways that you can organize your texture, your image, to make it so that it wraps the mesh, the 3D object, in such a way that it appears the way that you want it to. So in this case, making it so that it has the correct layout of the texture, the image texture on the 3D mesh. And then on this side, I have what's called a shader material, which allows me to write code using a language called GLSL, which lets me specify what color each part of the object should be at any given frame. So that's called a fragment shader. There's also something called a vertex shader, which lets you write code which defines where each of the points in my 3D object are at any given time. So using shaders is how the underlying graphics library works with your GPU. Shaders are programs that work very well on a GPU. GPUs are designed to be very parallel since they need to render all of these different pixels at 60 frames a second. It needs to do a lot of parallel processes. And so shaders are designed to take advantage of that, which is kind of why shaders are written the way that they are, why they have the limitations they do, but they're also incredibly powerful, being able to create these very dynamic textures that we have over here. Any questions at this point?
No, this is awesome.
Oh, I'm glad you're enjoying it. Give me just a second to see if I can figure out the camera situation. I'm gonna do a hard reload. Kick Code Sandbox in the pants. And then go to the next. Nope. Oh, yep, that's not right. Okay, well, we'll just keep trucking along. So this is where Three.js comes in. Three.js is created by a gentleman named Mr. Doob, who is uh, incredible. He's been working on Three.js for over 10 years, and it's become one of the de facto 3D libraries in the JavaScript ecosystem. It's used by hobbyists. It's used by NASA for some of their Perseverance rover preparation. It's used by big corporations and small hobbyists. And if you go to the Three.js website, you can find a whole bunch of projects and websites built with Three.js. Really awesome. You should definitely check it out. Let me just reload again so the camera can be in the right place. Okay. This is a sample of Three.js code. So we've got our scene that we're defining as a new 3.scene. And then we also define our camera. In this case, it's a perspective camera, which emulates the way that our eyes work. So the idea being that you have a point in space, and then you have your frame, which is what you're seeing out of. Uh, this is where you're seeing your view from, and then from that point to each of the corners of the frame extend lines out forever, and that defines what you can actually see. So we define the aspect ratio of the frame using, in this case, the inner height and inner width of my browser window. We have a viewing angle or a field of view, which defines how close the point is. Let me do it this way: how close the point is to that scene frame. So the closer it is, the wider the viewing angle is, and you can see things much wider. And then the further away it is, you can see a much narrower view. And then these last two numbers are the near value and the far value. So we can make it so that we can see very, very close to the camera, or and very, very far away from the camera, or anywhere in between. It is interesting to consider how this mimics human vision, because you have your eyeball, which has the cornea on the front, and then it has all of the rods and cones behind, and that is what defines your viewing angle, your field of view, is the distance between your rods and cones and the cornea. So just fascinating little bit of biology there being built into this. Okay, then we have a renderer. In this case, we're using a WebGL renderer. Three.js also supports a SVG or a CSS renderer, although the WebGL renderer certainly has the most capabilities. Sorry, let me turn off that anaglyph again. We set the size of our renderer to the size of our window, since that's what we want to render to. And then we're adding a DOM element to our body to make it possible to actually render it to the scene. And that's what we're seeing here. The DOM element is a canvas element, an HTML canvas element that you can shove whatever pixels you want in. In this case, our WebGL renderer is going to generate a 3D scene, shove those pixels into the canvas, and that's what we're going to see. Okay, now that we have all the basics, we can create our scene. So we're going to create a box using 3.box geometry. This just creates 6 points in space and two faces for two triangles for each of the sides of the box. So we have point here, and point here for one triangle, and then a point here, and point here for another triangle. And it does that for all 6 sides. And that creates our 3D object. Then we have to define our material. We're using what's called mesh standard material, which is what gives you the ability to adjust all of those different settings. It is a little bit harder on the GPU because creating realistic textures is a complicated process for the GPU. But in this case, for just a box, it's not a big deal. There are other materials that you can use that are a little bit simpler, have simpler algorithms, and produce okay effects and results. But mesh standard material produces better effects than those and gives you more control. Then we can combine our geometry and our material together and create what's called a mesh, which is that combination. And then we add our mesh to the scene, and that's what gives us our cube. Now, we wouldn't actually see our cube if it weren't for some light. So we create what's called a point light, which is a light that exists at some point in space and emits light in all directions. You can also have what's called a direction light, which points in a specific direction. That's what was creating those nice shadows before, was a direction light. You can also have a ambient light, which just floods everything with light. But it entirely depends on what effect you want to have. We set the position of our light. And one thing that I'm forgetting here is you also need to add your light to the scene because nothing exists if it isn't in the scene. And then we call renderer.render with our scene and our camera. So we know what we're looking at and we know where we're looking at it from and how we're looking at it. And that's what creates the scene here. The final step is to animate it, to actually give it some movement. So here I'm making the cube rotate. I'm using a request animation frame loop. I'm setting the rotation X and the rotation Y of the cube, just incrementing it every frame. And then with every frame, we also need to call the render method again so that we can see what's happening on the screen with every frame in the scene. Any questions about how we do this with Three.js? Obviously, this is a very simple example, and there's a lot of other things that you can do with Three.js, much more complicated things, obviously. But this gives you an idea for the basics of building something using Three.js. Let me reload this again because the camera moved. So next, we're going to talk about React 3 Fiber, which is a project by Paul Henschel. He goes by OXCAOA on Twitter, which see if you can remember that. Otherwise, I'm pretty sure it's this link is clickable. So when I post the slides later, you'll be able to find him if you don't already. Paul does a lot of really great stuff around React. React 3 Fiber is a React renderer. So just like React DOM renders React nodes to the DOM, and React Native renders React nodes to native elements on iOS and Android and macOS and Windows and whatever, React 3 Fiber takes React elements and renders it to a 3D view. And we'll see how that's going to work in just a second and why that's awesome. Let me just go to the next slide, reload the page so the camera can get in its place. And here we go. React 3 Fiber simplifies a lot of the stuff that you do with Three.js. It adds abstractions on top of both React and Three.js in order to make it easier to work with. So in this case, we're defining our renderer using React. No, hang on. I'm using React DOM to render this canvas element to the DOM. But Three.js or React 3 Fiber does its own rendering inside of the special canvas component that is provided by React 3 Fiber. Then I don't actually have to import the point light component. It is an intrinsic element, just like div or span. But in React 3 Fiber, it recognizes that point light is just something that intrinsically exists. This is the case for every Three.js object that's built into the Three.js library. React 3 Fiber recognizes these elements as intrinsic elements, so you can just use them. I specify a position for my point light with a prop, just like that. And then I have a box component, which is a custom component that I've created that also has a position prop that I'm providing. This is what my box component looks like. So I have a ref that I'm creating with useRef. I use the mesh intrinsic element to create a mesh, and that mesh has children, a box buffer geometry, which is the same as the box geometry that we used earlier, just slightly different, but the differences are not important. It takes an attach prop, which tells me whether this child is a geometry or a material. And actually, recently, this attach prop has become implied. It's inferred in many cases. So you don't even have to use the attach prop. React 3 Fiber will know whether you're passing in a geometry or material. And then the way that React 3 or the way that Three.js works is you instantiate your geometry by passing it arguments. And those arguments in the case of the box geometry are the width, the height, and the depth. So in this case, I'm passing the width, height, and depth as arguments through the arg props or args prop. So 111, it's just a box. And then we also have the mesh standard material, which I'm attaching as a material, and I'm assigning it the color of orange, which it looks very yellow to me. I don't know specifically why. Now you might be wondering, why are we using this ref here? Well, that comes into play when it comes to animation. React 3 Fiber gives us a use frame hook, which creates its own request animation frame cycle that we can hook into and do whatever we want. So in this case, this is my mesh ref. So I'm accessing mesh.current, and I'm setting the rotation X to be the same as the rotation Y, and I'm incrementing both of those by 0.01 every frame. And this rotation is happening entirely outside of React. We are not updating state. We're not calling the React reconciler, render loop, whatever. This happens outside of React, which makes it very performant. If any of you have ever tried to update something very quickly using React state, you'll find that React adds quite a bit of overhead that makes that difficult. But by doing it outside of React, we don't have that overhead. We're able to update the rotation of this object very, very quickly. However, by combining Three.js and React, we get some benefits. Specifically, we have access to the hook system for state if we want to do that. We also have access to the event system. So this mesh has an on pointer over and on pointer out handler for events that's going to update the hover. And if the hover changes, then we are going to re-render based on the hovered state with a different color for our object. So I can hover over this and it turns pink. I should have shown how to do this in Three.js because it's significantly more complicated in Three.js. You have to figure out where's the cursor in the canvas. You have to project a line from the cursor's position out from the camera in 3D space and figure out what it collides with. And then that tells you what object it is. And then you have to do all of the stuff in order to update that specific object to make sure that it has the right color. But in this case, it works just like you'd expect in React. You just hover your mouse over and it recognizes the event, and that's it. And that's because of the abstractions that React 3 Fiber provide. So that's React 3 Fiber. Anybody have any questions?
I have a question.
Hit it.
For the attach, you said it was like it defines the type that that it uses. I'm not sure why do we need to know the type if there's like mesh standard material will tell you that it's material.
Oops.
So why do you need to have both?
Good question. Let me get back to the slides. I accidentally clicked somewhere I shouldn't have. So you're talking about this attach prop here. And the question is, why do we need to add the attach prop when React 3 Fiber is able to infer it? Is that your question?
Essentially, yeah. I mean, I don't know how it works under this, it's like behind the scenes, but like if box buffer geometry is a component that is, it knows that it's a geometry, right? So it should be. I don't know.
Right, and that is the case now. In React 3 Fiber now, you can actually get rid of the attach prop, and in most cases, it will work just fine. However, in some cases, such as if you're creating a custom geometry, there's no way for React to know whether, or for React 3 Fiber to know whether that component is a geometry or whether it's a material or whether it's something else. It doesn't know what to do with it. Because let me go back just a little bit and see. Okay, it's a little bit weird, but we can see everything that we need to see. This line right here with this cube the way that we create a mesh is by instantiating a new mesh class with the geometry object as its first parameter and the material object as the second parameter. In this case, in React's case, we're just passing children, but it doesn't necessarily care or worry about what order the children are in. So I could have the geometry underneath the material, and you would still expect it to work the way that it's supposed to. What the attach prop does is it explicitly says this is definitely a geometry or this is definitely a material to make it so that there is no confusion and you don't have any problems. However, like I've said multiple times, that's not necessary in every case anymore. And so if you're working with Three.js primitives like the box geometry or mesh standard material, you don't have to add the attach prop. Does that answer your question?
Yep. Thank you so much.
Thank you. Any other questions? Okay. Let me move on just a little bit. Okay, so this is just a simple little demo. This is an app which I've literally been working on for 2 years now, but haven't made a lot of progress on recently. But it's going to be a small game built with React 3 Fiber with these atoms that can react. And maybe once the actual talk is over, I can show that to you right now or at the end. But for this, I have this component here that is a sphere geometry here that's purple and a sphere geometry here that's yellow. And then it has this cylinder geometry that's spinning around it that is doing its thing. And then when you click on it, it actually has event handlers that make it so that it energizes a little bit when you click on it. So it becomes a more energetic atom. And then eventually it's going to pop and goes back down to the lower energy level. And you can see here, the same way that when you read the Thinking in React documentation, it talks about building web pages with components and how you draw boxes around the different parts. You have a box for your header, you have a box for your body and your sidebar and your footer, and each button is its own box, defining the components. Well, in this case, we have different components that build up this atom. And we're able to take advantage of that component nature of this object because we're able to use React components with React 3 Fiber. So we have each of these individual nucleus protons and neutrons are their own React component with their own behaviors. Each of these electrons flying around the outside is its own React component. And then the entire atom altogether is its own React component. And so you can actually stamp out this component in multiple places. I think the camera just moved, so I'm going to reload. Okay, yeah, that's the end of the talk. We hit 30 minutes. I know that this barely even scratched the surface. I hope you enjoyed it at the very least and can see how awesome 3D graphics in the web are. React 3 Fiber is awesome. The team working on React 3 Fiber is doing all kinds of amazing stuff, making it possible to do Flexbox layouts in 3D and all kinds of awesome effects that you can just build in that are their own components. Maybe just for kicks, I'll pull that up and we'll look at it. So I'll post the links to this in the React Podcast Discord, but you can find Three.js, React 3 Fiber, a Three.js fundamentals course, which talks about the basics and kind of goes into how to build things in Three.js. And then this talk was built with React Spring, which has hooks for React 3 Fiber, making it really easy to do nice animations and transitions. So I hope you enjoyed this. And that's the end of the talk formally. But we can definitely talk more about this. I'm actually going to pull up some more stuff really quick. So,
yeah, I was going to say I've wanted to look into Three.js for a really long time. I just haven't yet. So all this stuff is super interesting.
React 3 Fiber definitely makes it easier. Like you have to learn Three.js and React because Three.js has its own API and syntax and stuff that React 3 Fiber kind of just takes and uses it in its own way. So lots to learn, definitely, but Three.js makes using or React 3 Fiber makes using Three.js a lot easier. So this is DryDRE, which is a library of Three.js components, React 3 Fiber components. So let me just open up. They've got a code sandbox or a storybook, which we can look at all of these things. So they've got a text abstraction, which makes it possible to add text very easily. Shadow there. They've got cloud component that just makes clouds. So that's kind of cool. An environment component that creates a spherical environment for your materials to create reflections from. A camera shake component. I actually haven't seen this one before. That's really cool. So a little camera shake there. They've got a bunch of hooks that can do helpful things. This use progress, which shows a progress bar as things are loaded. We've got a stars, which should look familiar. I was using this component in my demo, my slides. This shadows component, which makes it really easy to add shadows. You literally just add a component and boom, you've got shadows. It's like really slick. Bunch of different controls. So orbit controls, which makes you orbit a point. Fly controls, which makes it so you can fly around. Oh, it's not working the way that I thought it would. Oh, that's kind of cool there, making it so that the text goes along a curve. Anyway, there's all kinds of cool stuff. I'll leave it to you to check out the DryDRE, however you pronounce it. It's 3 in some language that I do not know. So anyway, that's that. This is that game that I was telling you about. Hopefully it loads and runs well. I haven't touched this in ages. So, okay, there we go. So the idea for this game is you've got these particles, and when they're supercharged and you click on them, they explode and send other particles out and create chain reactions like that. And just needs a little bit of finishing touches. So we'll finish that eventually. But I wanted to show you the atom. Here is that component. We have all of the particles on the inside. So at the highest energy level, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different particles. And then we have the 4 electrons that orbit it. And then it takes in all of these props. So it has a type prop that changes the way that it appears, size, which cell it's in, and just render all of these atoms, and it just works. It's awesome. Yeah, here's that electron prop, which has quite a good bit of logic inside of it for the way that it's supposed to curve and its animation, its rotation, and how it behaves. But all of it just gets wrapped up into a component with 1, 2, 3, 4, 5 props. And in the atom prop, we only ever use 1, 2, 3, 4 of those props. So just makes it so that you can compartmentalize things a lot easier than with Three.js by itself. So anyway, that's all that I have. Thank you for coming.
Alex, hey, thanks so much for everything. This was amazing. I was like tuning into this and my meeting, and I was just like the whole time I was just like, I don't want to be in this meeting. I want to be I want to be learning. So I'm going to be watching this like 4 times in a row after
Okay.
after I close this up.
Yeah, feel free to hit me up if you have any other questions. I'm happy to talk about it.
Yeah, honestly, I've been this is like I've been thinking about you a lot because I want to. I've been playing a lot of games that require dice with my kids, and I remember you posting a tweet to like rolling dice in in a 3D space. And I just remember thinking like that would be the coolest way to like build a little app that we can like just roll dice, because like dice are loud, right? And so
Yeah.
like you go play, a game that requires dice in a public space, and it's like you're a nuisance.
Yeah. Dice are actually so let me so there's my dice.
Oh my
I've
gosh.
been working on these dice just a little bit. And it's complicated because you got to figure out where to place the numbers so that they're in the appropriate position. So I don't have a D10 or D12,
Okay.
but I do have the D20. So
Oh my
that was
gosh, that
a
is so
feeble,
cool.
half-hearted roll. Yeah.
That is awesome.
Oh, and there went the D6. So
Just
fun fact, though,
right off
in
into
Google,
infinity.
you can say roll 2D20 like that, and Google will roll it for you.
Oh, hey. And I can choose different dice sizes?
Yeah. So if you were like a super fierce level 20, whatever, level 20 paladin, you can say roll 10d4. Be like,
Oh my
haha, I
gosh.
did 28 damage.
That's amazing. I like how it does the calculation for you too and saves you the micro math step there.
It does. It does. So there's a fun tip. Oh, looks like my D6 has finally come down. It's a 1.
It's a 1. Oh, Alex, thanks so much. This is amazing. You always have the most like creative stuff to share, and I appreciate that about you. Kind of exploring the edges of whimsy and in fun in the web space.
My pleasure. Thanks, Michael.
Cool. Thanks everyone for being here. Who's left? And yeah, we'll see you next time.
Catch you later.